Friends, very good morning to everyone. We were dealing with various aspects of reactions. In any reaction, a starting material reacts with a reactant and gives the product. In the process, the reactants are converted into product. In this process, there is an intermediate formed. The intermediates which are formed are of many types. One of them are carbocations. Today's subject of discussion is carbocations, its structure, bonding, stability, preparations, and reactions. Today we are dealing with the structure and stability of carbocations. What are these carbocations? Thus, we know that these are the reaction intermediates. These reaction intermediates are a carbon with a positive charge on it. It is C plus. The simplest of the carbocations are methanium carbocation that is CH5 plus, and ethanium carbocation, and so on and so forth. Until early 1970s, all the carbons with a positive charge were called as carbonium ions. At present, we are calling it as carbocations. Here, the carbocations can be classified into carbenium ions or carbonium ions. As we see here, this is an example for carbenium ion which is hypovalent in nature, and this carbonium ion which is hypervalent in nature. The carbenium ion is having CH3 plus 3 plus protonated carbons are carbenium ions. If they have plus 5 or plus 6, then they are called as carbonium ions. However, these carbonium ions are less prevalent than that of carbenium ions. The carbocations are having a sextet instead of an octet. In its outermost shell, it has 6 electrons than that of 8 electrons in the regular carbon. How these carbocations are formed? Carbocations are formed during heterolytic cleavage. What is this heterolytic cleavage? Heterolytic cleavage is one where the cleavage of the bond occurs in which one takes away the electrons and go, leaving the other electron deficient. Heterolytic cleavage of organic molecule when occurs, if the carbon donates that shared pair of electrons to the living group takes away the electrons and develop a positive charge on the carbon, and this gives rise to carbocation. Right? Carbocations. Structure is the discussion of today's class. Here, carbocation has 6 valence electrons instead of 8 in the regular carbon. Thus, it is having deficiency of 2 electrons. As it is electron deficient, it acts as a Lewis acid. It is in need of electrons. An electrons acceptor is a Lewis acid. It accepts electrons, that's why it can act as a Lewis acid. Carbocation is in sp3 hybrid form, and it has one vacant unhybridized p orbital. As it is in sp2 hybrid form, it is having a planar structure. It is coplanar in nature, in which all the 3 covalent bonds are spread across in a single plane. And it has a bond angle of 120 degrees between these atoms. Here this is the carbon which is electron deficient, that is carbocation, and the groups attached to it lie in the same plane, and there is a vacant p orbital here which is perpendicular to the plane of this system. The bond angle between the two R groups is 120 degrees. This is attached to three atoms only. That's why it is trivalent in nature. The order of stability of this carbocation is like this. Tertiary carbocations are more stable than secondary, are more stable than primary, is more stable than simple methyl carbocation. If we look at this structure in a 3D view, the carbocation exists like this. This is the carbocation carbon to which three atoms attached is trivalent. They lie in the single plane. This is sp2 hybridized. If I take a methyl cation, the carbocation carbon of the methyl cation is in the center. It is attached to three hydrogen atoms. They all lie in a single plane, and the vacant p orbital is perpendicular to plane of this ring system. This is how it looks like in a 3D form. This 2p orbital, which is vacant, this lies perpendicular to the plane of this carbocation system. Carbocations, as they are highly electron deficient, they are highly unstable. Immediately when they get a chance, they react and gives rise to a stable form. Carbocations are so unstable that they cannot be isolated at all. As they are so unstable, they are equally reactive. When a R is an alkyl group, carbocation gets stabilized. Carbocations, the simplest of all, is a methyl cation. The carbon, which is positive charge, attached to three hydrogens. If it is attached to one carbon and two hydrogens, it is a primary carbocation. Example is ethyl cation. The isopropyl cation is an example for secondary carbocation which is attached to two carbons and one hydrogen. If it is attached to three carbons, then it is a tertiary carbocation. Example is tertiary butyl cation. Tertiary butyl cations are more stable than secondary cations, is more stable than primary carbocation, is more stable than simple methyl cation. Why is it so? This is because of the different effects which is produced by the adjacent alkyl groups. One of the effect is an inductive effect. Because carbon in carbocation is electron deficient, it tries to pull the electrons from the adjacent carbon so that it becomes little more stable. If this is adjacent atom is an electron donating group, it can pull the electrons and it gets stabilized. If it is an electron withdrawing group, then it itself withdraws the electrons. As such, it is electron deficient, and the adjacent electron withdrawing group is pulling the electrons from this deficient carbon, and then it makes it much more unstable. Thus, an electron donating group adjacent to the carbocation donates electrons through its sigma bond, and it stabilizes the system. If there is an electron withdrawing group, it pulls the electrons, it makes this carbocation much more unstable. This presence of an electron donating group or withdrawing group in a ring system, it creates a permanent polarization in the molecule, and this effect through by donating the electrons through sigma bonds, and this effect is called as inductive effect. Because of this inductive effect, if it is having an electron donating group, it stabilizes the ring system. Alkyl group, it is a donating group. That's why the tertiary carbocations have three alkyl groups has more stability, whereas secondary alkyl carbocation has two alkyl groups, hence it is less stable. Carbocation is also stabilized by hyperconjugation. This is also a permanent polarization which is created in the molecule. This occurs when the adjacent carbon has a carbon and hydrogen bonding. This hyperconjugation effect is called as no bond resonance effect. The empty p orbital in the carbocation, it shares the electrons through the sigma bond from by breaking the carbon hydrogen bonding. Here, the carbon hydrogen bond of the adjacent carbon, it breaks, and when these electrons are taken away by the carbon, and hydrogen becomes H plus, and these electrons are shared with the vacant p orbital of the carbocation. That's why this is called as no bond resonance effect. Here there is no bond between carbon and hydrogen. That's why we call it as no bond resonance effect, and this is in turn called as hyperconjugation effect. Here, if I take a tertiary carbocation and a secondary carbocation like isopropyl cation, a primary carbocation, methyl carbocation, we can find hyperconjugative effect more in tertiary carbocation because it has three alkyl groups. Means each alkyl group contains three hydrogens and three alkyl groups together has 9 CH sigma bonds. And this can be broken and thus electrons are shared with the adjacent p orbital of the carbocation. That's why it stabilizes the system in a more better manner than that of secondary carbocation as it has only 6 hydrogens. In case of ethyl carbocation, that's a primary carbocation, it has only one carbon and that's why it has only three carbon hydrogen bonds and hence it is less stabilized than the previous one. Because of the positive inductive effect of the alkyl group and the hyperconjugative effect of the alkyl group, the carbocation gets more stable. These are the two factors which stabilizes the carbocation. If I take a primary carbocation like this, here it is positive center. These electrons are moved. The carbon hydrogen bond breaks C H plus and these electrons are shared with this vacant p orbital of the carbocation. Once the carbon and hydrogen is broken here, next the carbon and hydrogen of this gets broken and it goes on sharing. In case of a tertiary carbocation, there are three carbons. Here, the carbon hydrogen bond here breaks and this is shared with this. In the next, the carbon hydrogen bond here breaks and this will get shared. And so on and so forth. As there are 9 hydrogen attached to 3 different carbons, it can has more stability. Carbocations are also stabilized by resonance effect or conjugation effect. The resonance effect is also because of the presence of an electron donating group or an withdrawing group. In case of inductive effect, there is electron donating group or withdrawing group. But the sharing of electrons takes place through the sigma bonds. Here in resonance effect, they are shared through the pi bonds. That's the difference between the inductive effect and the resonance effect. Conjugation with multiple bonds or with lone pair of electrons gives the stability, it increases the stability of the carbocation. This is another factor which stabilizes the carbocation. Triphenyl methyl cation has three phenyl groups, and diphenyl methyl cation has, the name indicates, as two phenyl groups. That's why triphenyl methyl cation will be more stable than diphenyl methyl cation. Here, the pi electrons in the phenyl group moves towards the carbocation to satisfy the positive center. Once this electrons moves, this positive center is created on the carbon from which it has left. Then the adjacent electrons moves towards this carbocation and gives rise to another carbocation, and the process continues, and that's why it stabilizes the total ring system through the participation of this multiple bond. And this carbocation is in conjugation with this double bonds in the phenyl ring system. That's why it gets stabilized. Three factors are there which stabilizes the carbocation. First one is the inductive effect, second one is the hyperconjugative effect, another one is a resonance effect. If I take a benzyl cation and an allyl cation, benzyl cation will be more stable than allyl cation. Here this is a allyl cation. The pi electrons here moves towards this positive center. Once this electrons moves, the new carbocation is formed on the adjacent carbon. And the electrons are shared between this carbon and this carbon. And that's why it is stabilized. It is something like I have some problem and that is shared with others, and this sharing, it decreases the burden on it. That's why it becomes more stable. It is something like when we have something which is sorrow, we have to share with others. Then we get more stabilized. Even if we have happiness, we should share with others. It also gives us stability. In case of benzyl cation, it is conjugated with three double bonds of the phenyl group. The pi electrons here moves to satisfy this carbocation positive center, creating a positive center on the carbon atom from which the electrons have moved. Then these electrons moves adjacent electrons, creating a positive center, and this goes on. And that's why it has more canonical forms. More the canonical form, more is the stability. Here there are more canonical forms. Here only two canonical forms are possible in allyl cation. That's why it is less resonance stabilized, and hence allyl cation are less stable than benzyl cation. Likewise, phenyl cation or benzyl cation is more stable than allyl cation, is more stable than simple propyl cation, as it do not have this resonance effect. It can only have positive inductive effect and a hyperconjugative effect. If I take methoxymethyl cation and ethoxymethyl cation, which will be more stable? Here this is the methoxymethyl cation. This adjacent to this methyl cation, it is having an oxygen which is in sp3 hybrid form. It has a set of lone pair of electrons, and this set of lone pair of electrons, it gives that electrons towards the positive center of the carbon of the carbocation, and once these electrons are given to this become positive, and sharing of this lone pair of electrons takes place, and this is also a resonance effect. Because of this lone pair of electrons on the oxygen which is present adjacent to the carbon atom, it becomes more stabilized than that of methoxyethyl carbocation. Here there is no conjugation with this lone pair of electrons. There is a carbon atom in between, hindering this sharing. That's why methoxyethyl carbocation will become less stable than methoxymethyl carbocation. Sharing of with lone pair of electrons also gives rise to a stability. If I take tetrahydropiron, this is a carbocation at the second position. And here, this is also tetrahydropiron where carbocation is at the third position. First, second, third. It is at second position, this is at third position. Which will be more stable? Definitely it is tetrahydropiron with carbon which is having adjacent to it an oxygen which has lone pair of electrons. It shares its electrons. A resonance effect is created. That's why this becomes more stable than that of the third carbocation. Aromaticity is another factor which stabilizes the carbocation. For example, the vacant p orbital of the carbocation, if it is conjugated with the cyclic ring system, then it provides greater stability. Here there is a positive center in this ring system. The pi electrons in this ring system gets conjugated with this, and this has 6 pi electrons and one ring system. It follows Huckel's rule. That's why it becomes aromatic. Here also cyclopropyl cation, it becomes more stable because of the aromaticity. Cyclopentadienyl cation is not having a stability because it do not follows Huckel's rule. Cyclopropyl methyl cation is more stable than benzyl cation. Why is this so? In cyclopropyl methyl cation, it has a bent bond. This bent bond is also called as banana bond. And this bent bond sharing will be more effective than in this. That's why it becomes more stable. The neighboring group, if it has an electron donating group, it can stabilize as the carbocation. This is the carbocation stability by participation of the neighboring group. Here there is acylation, acetylysis, OTS create a carbocation. On the adjacent carbon group to this carbocation there is a phenyl group, and the phenyl group double bonds are shared with the adjacent carbocation, and a bridge is formed between the carbon two carbons, and that's why they are called as bridged carbocation. The phenyl group in the neighboring carbon is involved in the stabilization of the carbocation. There is an involvement of neighboring group, that's why carbocation gets stabilized. Hence, carbocation stability can occur by a participation of neighboring group also. And this type of carbocations, where there are bridge is found between the two carbons, one is the carbocation, another is the adjacent carbon. These are called as bridged carbocations. These are phenonium cations. These are the 5 factors which stabilizes the carbocation. Carbocations, as such, they are unstable. But however, because of the adjacent groups present in it, it can become stable through inductive effect or hyperconjugative effect or by resonance effect. If it becomes a part of the aromatic ring system, the carbocation also gets stabilized. Aromaticity is another factor which stabilizes the carbocation, and neighboring group participation also stabilizes the carbocation. These are the 5 factors which stabilizes the carbocation. That won't mean that they can be isolable. All are non-isolable. But however, they will be comparably more stable than a simple methyl cation. Next class, we can deal with other aspects of the carbocation. Thank you.